Hey, welcome to Passages in Applied Mechanics by Dr. Lorenz Garcia. Today, statics. Bending of beams, shear force and bending moment. In previous lectures we introduced beams as structural members, or machine components used to support transverse loads due to weight or other causes. The horizontal beams under this bridge surface will be supporting load forces perpendicular to the length of the beam. We learned how to calculate reactions at beam supports if all loads are known. It is time now to discuss the effects of applied loads on a beam and the relation between the conditions of loading, the cross-sectional dimensions of the beam, and the internal resistance in the material of the beam. Two concepts are required to be introduced: the concept of shear force and bending moment produced in a beam by the applied load, and also must learn to draw shear force and bending moments diagrams for beams subjected to various loading conditions. Normally a beam is analyzed to obtain the maximum stress, and this is compared to the material strength to determine the design safety margin. It is also normally required to calculate the deflection on the beam under the maximum expected load. The determination of the maximum stress results from producing the shear and bending moment diagrams. Let us define these concepts. Shear force. In this case, we must look at the internal forces that exist within the material of a beam subjected to loads. Consider two portions of a beam cut but an imaginary section traversed to the beam as shown in the figure. The effect of the unbalanced forces on each part of the beam is to move the left-hand portion upward relative to the right-hand portion, as shown. The reason that we never actually observe such movement between parts if a solid beam is because internal forces exist within the material of the beam in the plane of the imaginary cross-section which resist the tendency for such movement. Shear force diagrams. A graphical method of representing results, called shear force diagram, has been developed. It consists simply of plotting the values obtained by calculation against the distance measured along the beam. It should be noted that in the space between two adjacent external forces, shear force is constant irrespective of the actual position of the reference cross-section. The shear force diagram will therefore consist of horizontal straight lines, with step changes under each load. In other words, a shear force diagram is simply constructed by moving a section along the beam from, say, the left origin and summing the forces to the left of the section. The equilibrium condition states that the forces on either side of a section balance and therefore the resisting shear force of the section is obtained by this simple operation. The sketches show simply supported beams with unconcentrated forces, while these sketches show cantilever beams with three different load combinations. Bending moment. In addition to internal shear forces, every cross-section in a beam may also experience an internal moment called a bending moment. Considering the two portions of a beam, as we have before, cut in this case by an imaginary reference cross-section. As shown, another effect of the unbalanced forces on each part of the beam, not considered previously, is that the beam bends. The amount of bending tendency at the reference cross-section of all external forces on a portion of the beam to one side of the cross-section. The sum of all moments is called the bending moment. Bending moment diagram. Information about bending moments can be conveniently represented by means of a bending moment diagram, which is a plot of the values obtained by calculation, against the distance measured along the beam. It can be shown mathematically that in the spaces between two adjacent external forces, bending moment varies directly with the distance measured along the beam. The bending moment diagram will therefore consist of straight lines joining the points represented the computed magnitude of the bending moment at each load-bearing point. The bending moment diagram is obtained in the same way than the shear force diagramma except that the moment is the sum of the product of each force and its distance, x, from the section. Distributed loads are calculated by summing the product of the total force, to the left of the section, and the distance, x, of the centroid of the distributed load. The sketches show simply supported beams with unconcentrated forces, while these sketches show cantilever beams with three different load combinations. In conclusion, shear force and bending moment diagrams are analytical tools used in conjunction with structural analysis to help perform structural design by determining the value of shear forces and bending moments at a given point of a structural element such as a beam. These diagrams can be used to easily determine the type, size, and material of a member in a structure so that a given set of loads can be supported without structural failure. Another application of shear and moment diagrams is that the deflection of a beam can be easily determined using either the moment area method or the conjugate beam method. Let's apply these concepts to solve engineering problems. Dr. Lorenz Garcia here, thanks for watching. Ciao.